发现好像不要打破眼镜。8点不动啊？8点哦。OK。不要睡过了。睡过。不该给人家听，我们不爱给你玩的这种，我们要搞小学，要校园暴力。Jackie 本来不去唱歌，那徐静要去以后，马上哎，我已经发现。Alright, let's start. 卢哥，优惠。Yeah, quite a few. Exam 啊，later. 12 到今天叫我们离开专注。最后的时间咯，讨论题目。Okay. Okay. So before we start, I think quite a lot of you a bit confused on the idea of tangent plane of surface. What's linearization? Okay. Right. So let us recall a bit. What are these tangent line doing? So last time we mentioned that, let's say we have this curve here, x over x squared, for example, right? If we want to find tangent line, again, of this curve at this point, how does the tangent line look like? Horizontal, right? Okay. So this is the tangent line. So we think that this tangent line maybe only touching at one point. Okay. But what if my graph is fx equals to x? Okay. What's the tangent line at this particular point here? What's the tangent line at this particular point here? Just exactly the same line. Okay, this is the same line. Okay, you have the same line here. Right. Okay, so the secant you take here is constant, for example. Is it constant? Is it constant? Right, because if you do f prime x, it is just 1 always. Okay, so this one is the gradient, gradient of the tangent line. Okay. So similarly, if you have a flat surface, okay, you have a flat surface, what's the tangent plane on this particular point? Any point, what's the tangent plane? If you have a flat surface here, flat plane, what's the tangent plane at any point on the plane? Then guess. Just the plane, just the plane. Okay, let's compute it. Let's try and compute, show ourselves mathematically. So this is what maths do. Okay, when we think of one idea, okay, we want to compute it explicitly. Okay, so let's take an example of plane. We have made a plane example, which is this: 4xy equals to 6 minus 3x minus 2y. How do we decide this is a plane? Do you still remember how we decide this is a plane? We look at the level curve, right? We cut the surface using the xy plane, okay, at every level. At every level, we see what happened, okay? Like at level k equals to -6, you have a straight line, okay? K equals to 0, you have a straight line. K equals to 6, you have a straight line. K equals to 12, you have a straight line. So what does this number represent here? These represent the height of the line. Okay, so you can see that this line, okay, increase in height. So meaning your plane is like increase in height. Okay, so this is the plane. Does everyone agree that that function gives a plane? Okay or not? Okay, so how about let's find the tangent plane at 0, 0. Let us find the tangent plane at 0, 0 in this case here. Okay, so let's make one page. Okay, so let me try and draw this diagram here. X, Y, Z. Okay, so we have a plane, slanted plane like this. Okay, let's find the tangent plane at the origin. Okay, at the origin. Okay, for example, here. Okay, so meaning we want to find a linearization at this point. Okay, so what's the linearization formula again? Linearization of this surface. What's the linearization? Lxy equals to FAB. So let's say this is a linearization of surface at AB. Okay, FAB plus what? So in first variable, you differentiate once, right? Okay. In second variable, you also differentiate once, but you have two direction. Right? You have two direction. So you have one direction you can partially differentiate with respect to x. Okay, and then shifted your x plus Fy shifted by y. Okay, so this is the linearization or the tangent plane. Okay, at that point. Let's say this point is the 0, 0. So our f is fxy equals to 6 minus 3x minus 3 2y. Okay, and when is it f0, 0 equals to? So it's equals to 6. So in 3D dimension, this point is 0, 0, 6. Okay, so it's above here actually. So 0, 0, 6. To move out a little bit. 0, 0, 6. Here, for example, 0, 0, 6. Okay, so I urge you to imagine this diagram here 3D in 3D, okay? So please turn your head or turn your mind around and think of this as a 2D plane, and then this Z is coming up. Okay, either come in or come out. Okay or no? Okay, think of this plane is a slanted plane. Okay, slanted plane. So let me give a normal vector like this. Okay? Okay or no? Okay. All right. So what's the tangent plane here? Okay, how to find this Lx1? Okay. So f0, 0. So we're at. So let me fix our AB. So at 0, 0. Okay. Our Lxy is just 6 plus. To differentiate my function with respect to x, what do you get? Wait. I want to ask Roland again. So partial differentiate f with respect to x, what do you get? Yes, minus 3. Good. So we don't need to evaluate anywhere already because this is just a constant, right? Okay, and then x minus 0 plus fyab. So fyab is minus 2. Okay, and then y minus 0. Okay, so all together we have 6 minus 3x minus 2y. So do you get back the same plane or not? So you get back the same plane. So what does this mean? This means that my surface is linear. Is a plane linear or not? Yeah, plane is linear. Okay, plane is a linear object. Okay, plane is like a line that is linear. Okay, so you recover your plane using tangent plane. So meaning what? this tangent plane here can get all the point on your plane without adding the epsilon delta stuff. No need to adjust. Zero adjustment. Okay. It's not like this case here. Okay. If you compare the original curve and the line, you move away from this point, then you need to adjust to get back your surface. You understand? Can you see or not? So how to get? So now we have a goal. We want to recover our surface using my tangent line. Okay, because why? Because if I zoom big enough, it is just that line. But if I zoom out, you can slowly see the difference already, right or not? So I need to add more and more if I go away from the point I find the tangent line. Correct or not? Okay, but for the line, it is exactly the same line. For the plane, it is exactly the same plane. Okay, we don't need to do adjustment if I go anywhere else. Okay, so in the higher geometry, differential geometry, what we study is we study our surface using tangent space. Okay, generalization of this line and surface. We call it a tangent space. Okay, because when we zoom in large enough, it is just that space. It's the same space. Okay, but how do we put this space together to study a big surface? Right? Because for example, 听过盲人摸象吗？听过吗？ Okay, because you are human, you are so small. Imagine you are blind somewhere. Okay, you want to touch a big object like an elephant. Okay, so you go and touch. Okay, somebody said, "Wow, this is so big." Okay, and then so tall, and then the other said, "This is actually small and then flexible." And then which part they touch? Sorry. Yeah, leg the trunk elephant trunk, elephant leg, they are different. Or it's a white flat surface, elephant ear, right? So how I put all these local feelings together. Okay, so this is what we do in a higher geometry case. Okay, because it's too big. So the universe is too big. How do we study it? We study bit by bit, bit by bit, bit by bit, bit by bit, and then how to put these stitch them together and then understand the bigger objects. Okay. Okay or not? So this make these tangent plane, tangent line very important object to study. Okay or not? Okay. So this is about linearization of tangent plane surfaces. Okay. Let me see. Okay, and then the next thing we want to do revision on is the chain rule, right? Last time we finished at chain rule. So let's do a few more examples. And let's do a few more examples. How about we do a warm-up example with this? Okay, I'll let you try about 3 minutes. Okay, compute what is del u del x. Okay, at a particular point. Let's try and do this together. Let's try and compute this del u del x together. Hey, where's Seng? Huh? Juice.
Preparing for midterm.
Okay. Early preparation. Buy one, free one. Okay, try and compute this del u del x. Okay, as a warm up. So this question has an extra variable than what we discussed, but you should use the same tree method to construct the formula. A large, okay. Okay, have already get the formula first. Get formula already. So del u, del s. You got how many paths to go from u to x? 3, right? So you can go through ux, uxs, uys, and uzx. Okay. So each path here represent what? Represent a partial derivative. Okay. So from u to x, you have del u over del x. Okay. And then del from x to s, you have del. Anyway, too advanced already. Del x over del s. Okay. And then u to y, you have del u over del y. And then y to s, you have del y over del s. And then u to z, you have del u over del z. And then z to s, you have del z over del s. Okay. So this means what? You need to add the 3 paths together and then multiply the path when they concatenate to each other. So for example, del u over del x is the addition of 3 paths, where these 3 paths are the product of path from ux to s, uy to s, uz to s. So we have u del x times del x del s plus del u del y times del y del s plus del u del z times del z del s. Okay, so let me ask one person for Yanru. So why do we use del instead of d? Why we use del instead of d here? Because they different. What's the difference? Because the function have more than one variable. Okay, right. You see, so u, how many variables describe u? More than one variable. Okay, and then describe x, there are r, s, and t. So you need to tell me which direction they differentiate. Okay, so when we choose one particular variable, we use del. Okay, this is what called the partial derivative. So you just partially differentiate. You don't differentiate 3 directions together. Yeah.
So meaning if there's no y exact, but only x consists of r, s, t, right?
Yeah.
And
So
I differentiate u, I can write d x and then del with x del s.
du dx del u. Yes.
So I like the
Yes.
I can have d in the front.
Yes. 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 Correct. Okay. Yeah. Correct. But is that true or not? That formula? Is that formula true? I think it's true.
Assume no factor.
Assume no one. I know. Yeah, I know. So you mean, yeah.
That only implies partial duration.
Yes, there is for partial differentiation. That's right. That's the definition notation. Yes,
That's it.
that's it. Yeah, correct. So whenever you see there, right, you should think that this function should have other variable. Okay, for example, del u del x, meaning u not only written in x, u must be written in something else also. So in this case, u is also variable in terms of y, also in terms of z. Okay, in terms of s, y, z in this case. Correct or not? You see the question here. Is u in terms of s, y, z? Right, you have x, you have y, you have z. Okay, yeah. Okay, so can we quickly just jump to the answer? See you agree or not. I have 4 times r to the power 4, x to the power 5. Sorry, r to the power 5, x to the power 5, e to the xt plus 2 times r to the 5, x to the power 5, e to the xt plus 4r to the power 8, x to the power 6, e to the minus 2t sine qt plus 3 times r to the 8, x to the 6, e to the minus 2t sine qt. Okay, this is the answer. Let's check. You have 2 terms with sine, 2 terms with exponent. Okay? Okay, no? If you have problem, you just shout out loud. So I just keep continue first. So we want to evaluate this at where? R equals to 2, x equals to 1, t equals to 0. Okay, so you just sub values in. Sine will disappear because t is 0, sine 0 is 0. So you only left with 2 non-zero terms here. Okay, which is just 6 times 2 to the power 5, which is 192. Okay, yeah. Please check. Please check. Okay, so let's say I ask you to find del u over del t at the same point. What do you do? If I find del u over del t, what do you do? Huh? Use chain rule. What? Del s del t. Huh? Okay, change the del s to del t. So meaning you pick different path, right? You pick different path, right? Different 3 path. Okay? But what can you see here? Del u over del s is continuous. It's continuous, right? Is it continuous? Is it continuous or not? Del u over del x. Is it continuous? Is this function continuous or not? Polynomial continuous or not? Exponential continuous or not? Sine continuous or not? So product of continuous function is continuous. So this whole thing is continuous. So the other direction should also be continuous. Okay. At first, I want to say we can use the Taylor's theorem, but Taylor's theorems apply for what? For mixed partial derivative, right? Okay, but you can find that actually del u over del t, you should get the same answer. Is it the same reason or not? Yeah, you can check that actually del u over del t, you also get the same answer. Why? Del u over del t, you also get the same answer. Is it obvious why or not? Del u over del t, you get the same answer. Yes, you can try out. You can try the path method and compute it. The obvious one.
You mean that
Huh? Yeah, at the same point. Yeah, let me check. Let me check. Let me check. Let me check. Yeah, okay. So let me show you something. So I have did some computation here. Actually, we got the same equation here. Here is the same. So is it obvious why they are the same? X over delta t. Wait, let me see. What obvious why they are the same?
y is plus.
Or did I do something wrong? Del y over del t. Seems like I did something wrong, is it? I mean, this part here. I cannot point to you. Let me show you another picture here. Let's check. So here, this part here. Del y over del t is what? Del y over del t. So let's compute del y over del t here. Should be minus s squared e to the minus t, right? Correct. Okay, I think it's not the same. Maybe you need to check. Okay, let's check this like check. Okay, let's not deduce anything from here yet. Okay. Let me check these answers, see if they still get the same. Okay, but anyway, we can just stop at the del u over del x first. And then let's see. Okay, and then let's look at the other question here. Okay. Suppose that we have GST, okay, defined using F, okay, but F here have another two variable S and T, but it's S squared minus T squared and T squared minus X squared. And it says that F is differentiable, okay, because you need to differentiate it later. Show that G satisfy the equation here. Okay, so let's say your G is defined using F. So how do you compute del G over del X? So what do you do? So let me draw some tree first. So you have G, right? Initially you have S and T. Okay, if you know G, what do? You just differentiate G with respect to S, differentiate G with respect to T. Okay, but now your G is F of something. Okay, F of something. Okay, so what do you do? Okay, so what do you do? So similarly, what can you do? You can write it in two variables, right? Okay, so what's this two variable here? S squared minus T squared and T squared minus F squared. Okay, so these variable in terms are defined using S and T. Okay. So what's the difference here? So the difference here, maybe you want to look at del F over del of this big function or variable here. Okay, and del F of del T squared minus X squared, for example. Okay. But you see, so this is just a variable, right? Okay, what you can really do, you can just rename them, for example. Okay, you can rename them. For example, you let this is to be X, let this to be Y. Okay, you just rename them. Okay, it's fine. Okay. Is it okay? Are you guys okay with renaming the variable? Just rename the variable. Okay, so if we rename it, then it is easier to write it instead of repeating x squared minus t squared, x squared minus t squared. Okay. So in this case here, del x over del s becomes what? Become 2x, right? And then del x become over del t becomes minus 2t. Okay. They're just not just a partial derivative, but they are a function already. They are there's an explicit form of function. Del y over del x is minus 2x. And then del y over del t is 2t. Okay. So this is the tree we produce, okay, out of this. This is like a composite function. Okay, composite function. Okay. So in this case, how we compute del g over del s? Okay. So if you want to do del g over del s is equivalent to do del f over del s. Okay. So in this new tree here, how many ways to go from s? 2 ways. Okay, same 2 ways. So you need to add up the two paths and then take the product when you concatenate the path here. Okay, so in this case here we have del f over del s times del s over del x over del s plus del f over del y times del y over del s. Okay, so f we don't know because f is not given, but del x over del s we already computed. It is just 2s. Okay, and then del f del y we don't know because f is not given. But del y over del s we know, we already compute, which is minus 2s. Okay, and then all together we have 2s times del f over del x minus del f over del y. Okay, now. Okay. Okay, so similarly, in the same spirit, del g over del t, you should get 2t times del f over del y minus del f over del x. Okay, if you go through the same computation. Why? Why the negative swap? Because you can see that the negative appear differently if you go to the t path. Okay, can see or not? Can see or not? So the first path is positive, second path is negative. But if you go through the t path, the first one is negative, the second one is positive. And you can go through the same process and then see that this answer is true. Okay, okay. So altogether here, we want to verify what? T times the derivative with respect to s plus s times the derivative with respect to t is 0. So meaning you need to multiply t to delta g of del x plus x del g over del t, okay, which is t2x times del f over del x, okay, minus del f over del y plus s2t of del f over del y minus del f over del x. Okay, this whole thing here is just 0. Is it 0? Can you check whether it's 0 or not? So they have the same factor, right? 2tx. Okay, what you need to check is whether the thing inside cancel or not. Okay, so del f over del x, is it cancelling or not? Right, minus with del f over del x here. And then del f over del y cancel with the del f over del y here. Yeah, so this whole thing is 0. 0. Okay. Okay, any questions so far? No? Okay. So these are chain rule, different question, different type of question. Okay, should we go one more? Let's do one more before we leave the chain rule. So let's, if z equals to fxy has continuous second partial derivative, and we can replace our x and y using rs. Okay, find del z over del r and del 2z over del r squared. Okay, so we need to find these two things here. Okay, so this is kind of similar to what we had just now, right? So z equals to f of r squared plus x squared and 2rx, but they already renamed the variable for you already. Okay, x and y. Right? Okay, so there are two things you need to find: del z over del r and del square z over del r squared. Okay, so del z over del r is equivalent to what in this case? Del z over del r is equivalent to what? Yeah. Oh, wait. So what you are trying to give the full answer then? Okay, let's try if you can get the answer right. Okay. Okay. Plus. Mm-hmm. Okay. Guys, does everyone know how to get this formula here? Okay, similarly, what you do, you start with Z or F, right? Z is equal to F. Z and F is expressed in terms of X and Y. Okay, and then X and Y is in term in R and X. Okay, so what is R and X and Y in our case here? X is R squared plus 3x squared. Y is 2RS. Yeah. Okay, so there are how many paths from Z to R? There are exactly 2 paths here. Okay, and then each H represent a partial derivative. Okay, so this is the partial derivative that you take products. Okay, and then you sum them together. So out of these 4 factors here, right, only 2 factors you know. Okay, how to compute, because F is not given, but you are given what is X in terms of R and X. Okay, so what is del X over del R? It's just 2R. Okay, what is del Y over del R? 2X. Okay, good. So we have 2R here plus del F over del Y, 2X. Okay, so this is the answer. Yeah, this is the answer. So 2R del F over del X plus 2X del F over del Y. Okay, so this is the answer. How about second partial derivative? Okay, so far I only tell you how to write partial derivative, first partial derivative using this action. So how do you produce second partial derivative out of this method? What do you mean by same direction? Yeah. I only teach you how to do one partial derivative. So how do you achieve second partial derivative? Huh? What do you mean? What do you mean del z over del r? Hmm? What do you mean by del z over del r? Uh-huh. Okay, so you split del square z over del r square into what? Del of del z over del r del r. Right. So you treat del z over del r as another new function. Right? You treat it as a new function now. Okay, and then you partially differentiate it with respect to r. Okay. But we have already compute what is del z over del r, right? So we have del over del r over 2r del f over del x plus 2x del f over del y. Okay. So what should we do here? What do we get? What do we get here? How to differentiate that? So if I differentiate the sum of function, I just split it. Okay, I just split it in. So del over del r of 2r del f del y del x, because partial derivative is linear, so I can write like this. Okay, it's linear. All the derivatives should be linear. It's linear, so that's why it's also a linearization. Okay, so it's linear, so it's very linear. Okay, all the linear property. Okay, and then so how to differentiate this? How to differentiate this? Product rule. Okay. Okay. Good. So let's use product rule. So let's do the first one. Then maybe we will figure out how to do the second. So if I do a first one, I get 2 of df over del x. Yeah. And then plus 2r times del over del r of del f over del x. So how are we going to differentiate this guy with respect to r? So you need to think carefully now. Okay, so what is in terms of r here? Who is in terms of r here? It's in terms of r, but f is in terms of x. So what should we use here? Chain rule. Okay, so we have to use chain rule here. So how to use chain rule here? But okay, so let us be a little bit careful. So we have function del f over del x, right? Okay, so let me use color to draw these three. Okay, so this function here is defined using what? X and y first. Okay, and then x and y are in terms of r and s. Okay, so you apply the same thing. You apply the same thing. Okay, so you have two paths here. Okay, you have two paths here. So what do? So the first path you have del of del f over del x over del x. Okay, and then del x over del r. The other direction, you have del over the function of the function over del y. Okay, and then del y over del r. Okay, so this whole thing you need to write out again. Okay, you need to write this whole thing out again. So meaning I get 2 of del f del x plus 2r of so you need to take the product along the path, right? And then add them up. So if I go down the first path, I get del of del x and then del f of del x. So what is this? This is exactly del square f del x squared. Okay, so if I go down this route here, del x over del r plus del square f mixed derivative del x del y del x times del y del r. Okay, so this is what you get. Okay, so this is what you get. Okay or not? This is what you get. Okay, you do the same tree, but now your tree start with a partial derivative. First partial derivative. Okay or not? Does it make sense? Does it make sense? Okay. Any question or not? Okay. Question? Got question? Okay, now this is application of the tree just now to a more higher derivative. Is it okay? Okay. All right. Question? Just ask a stupid question is okay. 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 How about the second term here? We haven't differentiated yet. Okay. So if you do the product rule, one term will disappear because there's no r on 2x. Okay. Or you don't have product rule in this case. You just straight away do the differentiation. Okay. So the same method works. You will get del 2f del x del y del x times del r plus del square f del y square times del y over del r. So I urge you to try, okay, and draw out the tree for del f over del y. Okay, please draw out this tree here and then see that you get this combination. Okay, try and draw out this tree also. Okay, see that you get this combination. Does it make sense or not? Does it make sense? Try and draw out the tree, okay, and then see you get this combination. Okay. So how many paths you go from del f over del x to r? Okay, how many paths? There are 2 paths here. Okay, and then you get this combination. Okay. You know what to do? You know what to do? Does everyone know what you need to do to check? Yeah, please check. If you check yourself, then your memory will reinforce. Other than I just write it to you. Okay. So if you make mistake, even better. You make mistake, you know where goes wrong and then where to correct and then where's the important thing. Okay, do you know what to do to get the second term? Okay, you need to draw a tree from del f over del y to r. Okay, draw this tree. Okay, so all together you should get something like 2 times del f over del x plus 4r squared del square f over del x squared plus 8rx del square f over del x del y plus 4x squared del square f del y squared. Yeah. So you can check this final answer. Okay, any question about this chain rule before we proceed? Any question about the chain rule before we proceed? No? Any question? Yeah. Please check yourself for the green tree. Okay? Okay? All good? Okay, let's proceed. So next, we'll talk about this implicit functions with 2 variables. So why we care about implicit functions? So implicit function is a function that is, for example, f of xy equals to 0. So this is what? A function equals to a number. This is a level surface. Okay, this is a level surface. Okay, or level line. Okay, level curve, for example. Okay, so it defines y implicitly as a function of x. Okay, so for example, what kind of example we have? For example, this example here. Okay, this is an explicit function. Okay, so meaning we have y implicitly in x. So why we say this is implicit? Because we cannot write y equals to something. Okay, we cannot just extract the single y out in this case. Okay, so the at most we can do is this equation form. Okay, we cannot extract y, right? So if we were to extract the y, I think we should split it into at least 3 parts. Okay, yeah. Okay, so if we have this case here, then how do you find dy dx? Okay, because this is a level curve. Okay, you can find the gradient. So how do we find dy dx? So what the formula suggests here is you just do partial derivative of f with respect to x, and then do partial derivative with respect to y, and then divide them up. Okay, and then there's a negative sign here. Okay, so let me present you a slick proof. Okay, slick proof means this is not entirely correct, but quickly see why is it true. Okay, I mean it's true in general, but not all the cases. So we call this a slick proof. Later I'll see you the real implicit function. Okay, so let's produce a slick proof first. So suppose we have this function here, right? Okay, and then we can do partial derivative on the right. Last time we differentiate implicitly, right? So how do we do this? So how do we do this? So similarly, we use the same trick just now. So we got f, and then we return as x and y, and then the question says that y can be written in terms of x. Okay. So similarly, we can do like this. So we also got a tree now. Okay. Once we have this tree, so what does this edges represent? Right, these edges represent the partial derivative. Okay. So the first one, the top left, we have del f over del x. Okay, and then the bottom we have del x over del x, which is just 1. Okay, and then on the right we have del f over del y, and then del y over del x. So all together here, what do we have? We have del f over del x times 1 plus del f over del y dy dx. So here we change it to dy dx. Why? Because we know that y is only in terms of x, one variable. Okay, we don't need to put del anymore. This is equal to 0. Then rearrange it. Okay, rearrange it, you will get what is in the formula. Okay, rearrange it, you will get what you have in the formula. Okay, so this is a slick proof, but there's something wrong with this proof, but in general, it's okay. I will let you know what is the real thing and then we'll talk about it. Okay, so let's apply this formula here. Okay, so for example, we have this implicit function here. We want to find dy dx. Okay, so we use the formula. So the formula just now tells us that dy dx is equal to minus del f over del x over del f over del y. Do you know how to remember x is at top or y is at the bottom? Do you know how to remember? How? Roland, how? How? Huh? 印记啊？哦，印记。OK，不用印记，不用印记。So how to not memorize by heart? Wow, makes sense of English and Chinese. 印记. Okay, you don't need to by heart. Okay, you need to memorize by heart. So for example, you know division, right? What does division do? Division swap the fraction. Okay, so you can see that somehow this fraction cancel. Okay, but the special things here, there's a negative coming up. Okay, you must remember there's an extra negative here. Okay, if you want to use the above method to memorize, also can, there's a minus here because you move some terms to the other side. Okay. Remember, this is just a way to memorize. This is somehow like a chain rule. Okay, but chain rule also doesn't work like cancelling. So you shouldn't see these as a fraction, really. Okay, really they are not fraction, but morally it's like a fraction. Okay. So this is just a way to check you get the same right formula. Check the right formula. Okay. One thing about by heart is I say you are too tired. Okay, 适应 like 适应 too tired. If you by heart everything, too tired. Mathematics need to understand one. Once you understand, a lot of things you will get into. So do you forget red light is stop or green light is stop? Red light stop or green light stop? Do you just by heart? Yes. I mean, you already internalize the fact, right? So you need to internalize it. Okay, not just by heart. You won't forget already. Okay, unless you get dementia. Right? Very a lot. So you need to internalize. Okay, you need to ask why does it make sense? Why does it make sense? And then it will become make sense later. Okay. So if you by heart, too many things to by heart. Okay, memorize. Okay. Next, so how to compute this? So what is f in our case here? What is f? So formula tells you this already. So you need to find me what is x to compute. What is f in our case? How about write it at the top here? What is f? F is the thing that equals to 0. So what can you find that the thing that equals to 0? Here. X cube plus y cube minus 6xy. Okay, so your fxy is the 3 terms there. Okay, so you need to differentiate with respect to x and with respect to y at the same time. Okay, so if you differentiate with respect to x, what do you get? 3 x squared minus 6y. Okay, the bottom 3y squared minus 6x. Okay, so if you rearrange it, you get 2y minus x squared over y squared over 2x minus 2x. Okay, okay, or not? Yeah, this is just calculation. So what's this conceptually doing? What is this conceptually doing? Okay, talk about this, then we'll take a break, okay? So this is a real implicit function here, okay? So this implicit function is very important. We'll go to higher pure maths course. So you have to start from a point, a surface of a curve fxy equals 0, okay, and a point, okay, fix a point first, such that that point and that point is satisfied f(0), y(0) equals 0. What does it mean? This means that this point is lying on the curve. It satisfies the curve equation, okay, or the surface equation. Then suppose fx and fy are continuous, okay, and then there's a derivative with respect to y that's non-zero. Okay? Then this is very important because we want to solve y in terms of x. Okay, once the partial derivative with respect to y is non-zero, then we can solve y in terms of x. Okay, near the point p0. That is, I can write y0 in terms of x0. And then such that the equation f(x0) phi x0 still hold, okay, is on that surface or line. Okay. So for all the point that near x0, y0, okay, then we can find this formula. Okay, so this is the complete condition to get the formula, okay, to produce a real proof. And I put some remark there why we need to fix like this, why we need this condition. There are like 2 remarks that you need to take care, and then 3 remarks I put here. This is extract from your, I forgot it's which textbook, either it's Adam or the other one. Yeah, yeah, one of them. I extract it up. If you are interested, you can have a look. Otherwise, in this course, we just need to compute. Okay. If you care why is it true, then try and read about these. Okay. So the key part here is here. Okay, the key part is here. You need one of them is non-zero. Okay, fy is non-zero, so that you can solve y in terms of x. Okay, so this idea is very interesting. How do I say interesting here? How do I say interesting here? Let me think, how do I present to you? Okay, so did you learn Gaussian function or not in probability? Have you learned yet? Have you learned yet? Gaussian function? Have you learned or not? Have you learned yet? Now, I think it's called e to the minus x squared plus y squared. Have you learned this? Not yet? Not yet. Or minus y squared. Not yet. The shape is something like this. So let's look at this fxy. So the shape is something like this. It's a plane, but it come up a bit on the origin there. Gaussian distribution, if I'm not wrong. Huh? No, never see this. You can go and find it. Three blue, 1 brown. Talk about it. Yeah. So so what's the essence of this implicit formula here? So it says that y can be solved in terms of a function x. Okay, so you can see here. Okay, everything here is like in terms of x and y. But if I go deep to the top here, okay, somehow I can just describe this as a function of y equals to x squared. Okay, something like that. Does it make sense? Does it make sense or not? So how do I make this make sense? I don't have a round thing. Someone has round stuff or not? Round. I need a round stuff. Anyone have round stuff? Oh, I know. Got. Yeah. Okay, so if you want to describe this part, right, again, you will use maybe two variable function, okay? But when we just focus on this point here, we can just use y equals to x squared, for example. Okay, we have a curve here. How is it y equals to x squared? Y equals to x squared like this, right? So I just make it the other way, for example. Okay. So locally it's just a curve. Okay, locally it's just a curve. Okay, but if you want to destroy the whole thing, then you need to use a two variable function. Okay, but locally you can solve y in terms of x. Okay, this is the point of the basic function. You don't already throw away rubbish. Okay. Okay. So this is the idea of implicit function theorem. If you want to go deeper, if not, you just know how to use it. That's all. Okay. Any question on this? Any question on this? No? No one? No? Hmm? ULS, yeah. Correct. Yeah, ULS. Correct. So there's the condition here. Y is implicit of a function of x. Okay, so that means there's no other variable involved already inside my fx1. Hopefully we can later we can get into the video of the god again. Why the god can climb up the steep mountain wall. Okay? Yeah. Okay, so let's take a break until 212. 212.
这个东西啊，
点没？
它其实是跟这个一样的东西，是因函数微分，是这样子就这样子理解。
我想一下哦，这个是我们就给一个 formula 咯 ，instead of 你再从头算咯，对不对？这个我们就给一个 formula 咯，直接算咯，不像之前那样子做。
如果这样子的话，
等一下给我看一下，
就是因为这个它是 x 跟 y 吧嘛，
对，
然后以函数微分的话，就是我可以直接是微分的，然后就如果我是 dy dx 这样子的话，就是 x 的我可以直接做微分，然后 y 的我也是可以微分，把它没有 x 的话，我去乘上一个 dy dx 给它，然后这个就用它 product rule 就是一样的。
哦，是，啊，是确实，
去想，
直接
用这个东西来想。
OK，这样，你这个跟这个是一样的，其实，你只是把这个多余，你如果把这个东西引过来，你就是在做我这些东西，对不对？啊，其实是一样，因为你这个移过来就是在做这些步骤，全部做到完，所以你算到这边了，所以我就说这个是给你一个 formula，啊，你也可以这样做
OK，
一
样啊，有没有？
样的，呀。但是这个东西会比较有用，为什么有用呢？因为通常我们 define 一个 surface，我们会这样 define，我们不会这样 define，
明白。
我们会自然而然会有这个东西先，
明白。
对，
可以。
OK，
谢谢。
呀，
这个是上个星期选的那个，我是想要放这个，然后给它打到这个啊，without M 跟 N 的 info。
你这个换成 definition 哦，不要这样子，就打成前面一句就是对，好，这里是什么套路？来，什么一分半？
就是这样子的。
没有，我讲不要这样子表达，很乱
哦，
啊。你这边先写 definition 什么是一分半就是这个很乱，你下面直接用。
就是放这个进去，我可以证明到是换。
然后这么就可以了。中国人说
它在 cost 里面，
，my cos x 不是等于 cos minus x 吗？对，所以
我就可以把那个负号打掉。
可以不是？因为 cos of 你 x 你的减搬过来嘛，要不是减 of 那整个东西啊，这样减 of 那 cos 减 of 那整个东西不是等于 cos of 那个，
就变成是一分了。
所以它是 even 还是 odd？
我是要证明那个 odd，
它好像不是 odd，它好像是 even。But at 那个 interval 它是 odd 的，
得分还是 odd。
是这样讲。都是比如说，我也搞清楚。OK，不然为什么 cos normal 的 cos function 是
我是打算把它拆成这样，但是我拆了，然后把那个负拿掉嘛，拆了过后，接下来我不懂了。
我记得，我记得 cos of x over l from minus l to l 是零，为什么？怎样把 constant 去掉呢？记得 a 零还是 cos of 啊，i x over l 的 m 派 x 嘛，对吗？
是那个 OK 吧，我这边应该有
有吗？有吗？
上面这边有哪一个？
有一个新歌的，
新歌的是
新歌，
这个吗？还是
不是新歌吧？cos 跟 sin
哦
有啊，不是？
我这边没有，我这边没有写。
那个找一下，它的原因应该是跟这个一样，就是哦，这边没有哈，没有。但是你的 assignment 不是有用到吗？
这样子，
对。你什么时候把那个减 L 让 L 变到零到 2L 这边？OK，yeah，
所以我
所以
就不要过这边删。
make sense。然后你这个
对，
这么减 L 忽然间变这个，然后忽然间又变这个，
没有，我那边写错，我应该是要把2拿掉。
二拿掉，然后零，也不是哦，OK，OK，明白，所以这个二是错的。
2是错的
OK，
拿掉2，因为它是一分嘛，
要，说这边应该是 obvious 是零吧？哎，你算到了
3是0
啊？对哦，这个哪里来的这个？
啊，
这个哪里来？这个不是就是你刚才要的东西吗？
对，这个是我之前自己来我自己算的 就是我用这些 property，然后我用 identity，然后
对呀，
integrate
这个是你要的东西哦。对啊，
Yeah
这是你要的东西。
我是想要来从
可是问题是，他这个意思有讲，然后他是吗
我有讲 science or
？sin 是 odd，cos 是 even，所以 cos 乘 sin 就 even，
这个
但 even 乘 even 的话
对是
是 even 诶，
如果是 sin 乘 sin 或者是
就变 odd。
cos 乘 sin 的话，就是比较容易去解释，就是比较容易去解释它是 odd function。
耶，
这个
但是
cos 的
应该不是，它不是 odd 的原因。嗯，
我遇到是 odd 的，这样讲。
怎么知道它是 odd？
如果我用 to 的话，是我有办法去 observe 它是 odd 的。
哪里？看一下。
假设 cos cos 2派 x，
是
诶，这个也是 even 的。
even 不是 ？Yeah， 它是 even。
x 我刚刚没有错，哦 even
是 even。那为什么它 integral 是零？understand。
这个呢
先上先
？OK。
，OK。Okay, so finally we go to the stage of directional derivative. Okay, directional derivative. What's going on? Okay, let's go to directional derivative. Okay, so how to think about directional derivative? Huh? So let me draw a diagram first. Let's draw a diagram. Okay, what diagram you want? Let us draw circle. Can we have something not symmetric? Not symmetric one. Can we have something not symmetric? A surface that's not symmetric. Let me think. 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 What surface are not symmetric? How about draw a cylinder? Cylinder? Okay, let's draw a cylinder. Okay, let's draw a cylinder. Okay, let's draw a cylinder on this direction. Okay. So let's say we look at this point here. Right? And then if we go the x direction, okay, let's fix our direction x, y, z. Okay, if we go x direction, okay, let's not pick the top point. Okay, pick a slightly on the you get what I mean? So like this. So I got the cylinder. I don't want to pick the top point. Okay, I thought pick a bit away from the top. Okay, I just pick away from the top. Okay, got a gradient. I want to get some gradient. Okay, So if I go along x direction, so if I cut it, so maybe like this, right? Okay, so if I cut along x direction, what happened? Okay, we got a gradient like this. Alright, okay, we got a gradient like this in this direction. Okay, but if we cut along y direction, we cut along y direction. Okay, we cut along this one. So on this way, it is just constant. Correct? If I move along x direction, it is like moving around the circle. But if I cut along y direction, it is just flat. Okay, so along y direction, it is just flat. Okay, but is this the only two way I can cut the surface or not? No, I can, what can I do? I can just try and cut this way and then cut vertical way. What else I can do? I can cut it this way also. Right? And then I can cut in y equals to x squared like this. So I have a gradient, something like this. Choose the other color. So something like this. Okay, I can cut it in that way also. Okay, so if we cut in different way, all these different directions, we call it a directional derivative. So you see, now I'm just describing to you how to cut it, how to cut it, how to cut it. So in mathematics, we want to compute. We want to compute stuff. Okay, that means we need to define things that we can play around, algebra, number. Okay, so how we define this? Direction here? Okay, so this direction is defined as this. So let me see. So okay, so P is the new point we fix now. Okay, P is the direction, the point we interested in. Okay, so we label these terms here. P is the AB we fix. Okay, in the picture just now, this point, okay, correspond to a point on two-dimensional, which is AB. And then this top point here is FAB. Okay, so all together, the point we look at just now is A, comma, FAB. Okay, no? Okay. Usually we just talk about AB, AB, AB. Why? Why we just care about the point in the domain? Because we just fit the point in the domain into my function. And then the function will tell me the value of it. Okay, so FAB. AB, FAB. Okay, so how do we define the original fx and fy? Okay, we just make changes, okay, in the x direction, which is hi. Is linear algebra using ijk or not? Your linear algebra use ijk? Yes or no? Or E1, E2, E3? Also got, both got, everything got. Okay, so these are the same thing. So let me tell you this notation here. So we have, for example, this is two-dimensional case. So in two-dimensional case, you need two bases, right? Okay, so the standard basis we pick is what? E1 and E2. So what are E1, E2? E1 is 1, 0. E2 is 0, 1. Okay, sometimes you see as I or J. Okay, these refer to the same thing. Okay, they refer to the same thing. So, how do you define fxp? So recall what we had for fxp last time. Do you remember or not? What do we have for last time? So let me put AB here. So still can recall what we had last time? Column. So f of what? X plus h. Y. Sorry, here is AB now, right? AB minus f AB over h. Okay, so you need to compare here. What's the difference here? So the difference here is the first term here. Maybe not too obvious. Why is it the same? Can you see why are they the same or not? And why are they the same? P is AB, okay, plus h time 1, 0. Okay. So what is this? This is just A plus h comma B, which is the same thing. Does it make sense? So, one way to one difficult way in this course is you need to swap between vector notation and the normal non-vector notation. Okay. So the first here is not is called the vector notation here. Okay, vector notation. So the bottom one is just some variable, n variable. Okay, but you can write this n variable as a vector form. Okay, so p plus hi. Does it make sense? Does it make sense? Does it make sense? You know how to read this? Anyone have problem reading this? Yeah. Any question? P plus hi is AB plus H12. Any question? No? How about the rest? How about the rest? Okay. How about let me test? Okay, test someone. So what is P plus Hj? Let me ask someone. Ivan? What is P plus Hj? What's P? P is here. Okay, P is here, and then J is here. So what's P plus Hj? Linear algebra, this one later got test. Linear algebra, vector addition only. Okay, one maybe confused way is why suddenly I put this bracket, why suddenly I put this square bracket. These are same, referring to the same thing. Okay, I can also write bracket ABS like this. Okay, but in linear algebra, we prefer this. In calculus, we prefer this. Yeah, but they are equivalent. Okay, so what is P plus Hj? A comma B plus H time 0, 1. Okay, so all together, what do you get? P plus H. Okay, so does this match up with the previous definition or not? What's the previous definition for Fy? Can you recall? Can you check back? What's the previous definition for Fy? Okay, is everyone agree with this calculation here? Agree or not? P plus Hj. P is this vector here, and then J is this vector here. Okay, so if I plug the whole thing in, what happened? Okay, if I plug the whole thing in, F, Y, P, okay, is equals to limit of lim go to 0, F of A, comma, B plus H. Okay, I switch between the vector notation, minus F, A, B over H. So this is exactly the definition we had before. Okay, we make changes at Y. Okay, we make changes at Y. Okay, so this is the partial derivative in Y. Does it make sense? Make sense or not? Okay, so the hard part, one of the hard part about this calculus 2 is you need to combine linear algebra and calculus of one variable, single variable. Okay, so we combine these two. Okay, no? So instead of differentiate with respect to one direction, you need to differentiate with respect to the other direction, more than one direction, two direction, three direction, four direction, five direction, in n direction, you need to differentiate, integrate, okay, check continuity, and then so on. Okay, so this is the generalization of first one variable calculus. Okay, okay, now. Okay, so what do you see here? What's the difference here? The difference here is we take different vector that add the changes. Okay, so we can make this vector into any vector we like. Okay, in two-dimensional space, and then we call it U. For example, we call it U. Okay, we can take limit of fp plus a small change in the direction of u, okay, minus fp over h. Okay, the rest is the same. What's changing is the direction of your I and j. You pick the linear combination of I and j, okay, in the direction of u. So why is it unit vector? Later we'll see why we want unit vector, okay, instead of any vector. Actually, any vector will work, but unit vector will give us a convenient way to do work. Later we'll see why we use unit vector. Okay, okay, okay. Can understand or not? Understand? Okay, we make changes in arbitrary direction u we like. So for example, this picture here, we have a blue surface here. Okay, we can find derivative in any direction we like. Okay, and then if we fix the direction, that means we take a surface, or not surface, exactly a plane, and then cut it, slice my surface, and then when you have two surfaces slicing each other, intersection of two surfaces, you get a curve. Okay, and then at the curve level, then you will get the tangent line. Okay, so for example, at this point here, the tangent line is like this. Okay, at the other point, you have different tangent line. Okay, or not? Intersection of two surfaces, you get a Ethan, what do you get? Intersection of two surfaces. Yes, you get a line. Okay, either you get nothing, either you get a line, or you get a point. Okay, and so you will reduce. Okay, reduce. But if they are the same, of course, it's the same surface. Okay, so you get less than or equal to the dimension that you started with. Okay, okay. Okay, next. This is the theorem. We will attempt to prove this, I guess. Let me see, should we prove this? So this proof is appeared as an exam last year. Okay. So this theorem is I tell you how to find directional derivative. Okay, if not, you need to go to the limit definition. Okay, we don't want to do this. In this course, we almost never go to the first principle to find the directional derivative. Okay, we give you a way, we give you a tool to find it. Okay, so how do we find it? So you have to start with a differentiable function first. Okay, so that I can differentiate your function, and then f has a directional derivative in any direction u. Okay, as long as your f is differentiable, then I can find any directional derivative for you. How to find it? Okay, how to find it? Okay, so directional derivative is a function or a number? Is a function or a number? Is it a function or a number? Directional derivative. It is a function and it is a number. So when is it a function? When is it a number? When you evaluate the directional derivative at a point, you get a number. That number is the gradient of the line. Ms plus c, right? M have to be a number. Okay. Yeah. If you evaluate at that point, it's a number. But if you consider how all the gradient line change, it becomes a function. For example, differentiate x squared. What do you get? 2x. 2x tells you what? At different x, what is the gradient? Okay. So actually, it's a function in general. Okay, function from where to where? Function from where to where? In this case here, function from where to where? R2 to R. Okay, so it actually is a function from R2 to R. So in general, it's Rn to R. Rn. Yeah. Okay, because we only live in the R3 case. Okay, so this is a function from R2 to R. Good. Okay, good. So it has to be equal to some function of R2 to R. So how do we put this number together? is actually very easy. So why is it easy? It is just the x partial derivative, okay, times a, the direction you look at in x direction, plus y partial derivative times the y direction look at. That's all. You don't need to go through all the thing stuff. So that's why the x partial derivative and y partial derivative is very important, because you can use these two functions to build out any direction you like. Okay. Do you understand this theorem or not? Okay, to find any direction, what do you do? Okay, you have a direction AB, so you just take A, multiply the x partial derivative plus B times the y derivative. Okay. 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 Okay, so why is this true? Maybe we don't prove it today, because maybe you are too tired. Let's prove it next lecture. Let you absorb the result first. You believe first, then I show you why it's true. Okay. Okay now. Think about it. How to use it? Let's see. Do we have an example of using it? And then in the next lecture, I will show you why it's true. Okay, I let you sink in first this idea. Okay, think about this idea. Meditate on this idea. And try and meditate on this idea. Let me see what's next. Okay, meditate on this idea. We'll do exercise first, and then next lecture we come back and prove this. Okay, so let's try an example of this. So let's just get some confidence on this theorem here. Okay. We have this surface, okay, defined by this function here, s cubed minus 3xy plus 4y squared. So we want to find a directional derivative at 1, 2. Okay, 1, 2 on the domain. Okay. And then if you plug 1, 2 into this function, what do you get? You just get 0, I guess. Not 0. So let's compute. F12 is what? 1 cubed minus 3, 1 times 2 plus 4 times 3 squared. So what is this? 6, 1 minus 6, 9, 9, 9, 4, 36. So this thing is 31. So that's the point of 1, 2, 31, something like that, for example. Okay. We want to find tangent line on this point. Which direction? Right. They are like 360 direction. Which direction you want to pick? So this direction is making an angle pi over 6 with the positive x-axis. What is this? So let's draw this. So we have a 360 direction. I will call domain plane. While pi over 6 with the positive x-axis. So somewhere like this. Okay. So I will use this plane to cut my surface here. Okay, and then if I have the intersection of these two somehow orthogonal, okay, orthogonal to each other, right? So what surface I get? I get a line. So I get a line. So once I get a line, I want to ask about the tangent line. Okay, I want to ask about the tangent line, which is the directional derivative. Okay, so what do we need? What do we need for this theorem to find? So to apply the theorem just now, we want to have f is differentiable. Is f differentiable or not? It's obviously differentiable, right? Because this is a polynomial. Okay, you can differentiate. For this case, you can differentiate 3 times. Okay, everything will disappear. So by theorem, what do we have? Let's put out the formula first, and then we will decide what to do. Fxy equals to fx xy times a plus fy X, Y, B. Okay. So what is AB? AB is the direction we want to differentiate. Okay, or we cut the surface. So in this case here, what is our unit vector? They just tell you the angle, how you get the unit vector. Cosine. Wow. Okay, good. So your A is what? Cos power 6 and sine power 6. Okay, but we need a unit vector, right? Is this a unit vector or not? No. Sine square pi over 6 plus cos square pi over 6 is it 1? 1, right? Okay, so you need to find a unit vector line on the unit circle. Okay. Yeah. So this is like something from complex number stuff. Just that we don't care about the I. Okay, so what is A and B in this case? Is square root 3 over 2 and 1 over 2. Okay. Fx with respect to x, what do you get in this case? Yeah, maybe ask Roland again. So differentiate f with respect to x, what do you get? Differentiate function f with respect to x, what do you get? 3x squared minus 3. You sure? Don't tell him, don't tell her, don't tell her, don't tell her. Huh? Huh? How many variables here? X. Y? How about Y? Y? You need to treat Y as a constant. So if you differentiate minus 3xy with respect to x, what do you get? 不知道 Y 不知道Ethan 他不知道怎么办
Just ask our lecturer.
so what does it mean by we treat y as a constant? So meaning it's just a number. Okay, so you differentiate a number times x, you get a number back. So if you differentiate minus 3xy, you get minus 3 1. Okay. Okay, keep forgetting, don't memorize. Okay, so if you differentiate minus 3xy with respect to x, you get minus 3 1. Okay, similarly, if you differentiate plus 4y squared with respect to x, what do you get? What do you get? Any x or not? No x. Y is a constant or a variable with respect to x? Yeah, constant. So you differentiate constant with respect to x, you get? Yes. Okay or not? Please remember, okay, so you get 0. Okay, times a is square root 3 over 2. Okay, how about differentiate f with respect to y? Ethan, quick. Differentiate f with respect to y. 是应该开始笑人了。Differentiate f with respect to y. Can see f or not? F here, f here. Can see f? With respect to y. Yeah, minus 3x plus 8. Okay. But this one? 1. Times 1 over 2. Okay or not? Can check whether his answer is true or not. First term, x cubed, there's no y. Okay, x cubed is a constant with respect to y. So you differentiate constant, you get 0. Okay, and then second term is minus 3xy. So minus 3x become a constant. Okay, so you differentiate constant times y, you get the constant. We have minus 3x. And then 4y squared is the usual differentiation. Okay. All right. So what else? So what we want to do is we want to find at the point 1, 2. Okay, at 1, 2, what happened? You just sub everything in x and y. Okay, so if you sub things in, you get 13 minus 3 square root 3 over 2. Okay, sub x equals to 1 and y equals to 2 into the formula. Okay or not? Any question? You can try and compute yourself. You can try and compute yourself, check whether this is true. So it's like 3 times 1 square minus 3 times 2 square root 3 over 2 plus minus 3 times 1 plus 8 times 2 and half equal to this number here. Okay. Yeah. Okay. So this is the gradient. Okay, the gradient. Okay, gradient here, which is 13 minus 3 root 3 over 2. Okay? Okay or not? Happy? Happy? Yeah? Not really. Why? Why not happy? Okay. Okay. Okay, right. So let's continue. Let's continue. Okay, let's continue. So we can introduce another term. Okay, gradient vector here. So what is gradient vector here? So, so you see, look at this formula again. Meditate a second time. Okay, there's a product there. There's an addition there. What does this mean? What is this? What the heck is this? Linear algebra. When you need to multiply, when you want to add together. Huh? Subspace. Not quite yet. Combination. So how to combine? Why combine this way? How to combine in this way? You see, AP is coming from the same thing. It's coming from a vector. Then when do you split the vector stuff out into sum with product in linear algebra? Why not? When you split your vector into product form, sum form. Huh? Not quite. Not quite. Matrix 2 a little bit too big. We can use a smaller stuff. Dot product. Okay, we can rearrange this in the dot product form. Yeah, for example, we can pick fx and fy. And if I take dot product of these two vectors, then we'll get the formula. Okay, so this means what? This means what? This formula actually comes from some vector operation. Okay, and then we will call this vector here the gradient. With the gradient vector of function. Okay, so you see in one variable case, gradient and what's the word? Gradient. What's the other word to describe gradient? Slope. Yeah, slope. Correct. Slope. Gradient, slope are the same thing. Okay, but in two-dimensional case, gradient become a vector. In higher dimensional case, gradient is a vector. What is slope? Slope is the number that you evaluated. Okay, so the slope become this directional derivative. Okay, if you evaluate So if you evaluate du, you get slope. Okay, but gradient is a vector. Okay, gradient is a vector. Okay, okay, slope and vector. Right. Let me see. So okay, so this is what's the next content here. Okay. So del f duf is equals to we call it a nabla f. Okay, we call the gradient nabla f. Nabla. Okay, nabla f. Nabla f. Okay, nabla f. Are you guys happy with this notation here? Happy with this notation here? This is also this square bracket. Anything you want to write? But in calculus, we prefer this term. Maybe because they develop in a different way, so they use different convention, but actually they are the same thing. Okay, Anna? Okay, how about let's jump to the God stuff and then we will finish. So what's about the God? Okay, the God is this thing here. So maximum rate of change. Okay, we'll do this exercise in the next class after I introduce the proof. Okay, and then we will strengthen your memory. Okay, let's go to this new fact first. So a function increases most rapidly at p in the direction of the gradient with the rate of gradient. Okay, so what does this mean? So this means that your du f at a point p. So this is what we call a slope just now, right? At a point we evaluate already. This becomes a slope. Okay, when is this number the greatest number? Okay, when is this the maximum? Maximum, right? Your linear algebra asks when is it maximum. Okay, so this just now we have this formula is nebula p times the direction of u. Times here means dot product. In vector, there are two forms of product: dot product and cross product. But cross product will give you a vector. Dot product give you a scalar. But we want scalar here because this is a function from R2 to R. So we use dot product. So what is this? Test linear algebra, dot product. What's the formula of dot product? Dot two products together, what do you get? See? 等什么？你让金生笑了。Okay, what is dot product formula? Dot product tells you the angle between the two formula, but how to give the angle? Yeah, you don't. Yes, and then over what? Yes, the product of the norm. Okay, so the dot product is the product of the length, in other words, the norm. Okay, and then time cos theta. Theta is the angle between the two vectors here. Okay, because these are vectors. This is a vector, directional vector. Okay, directional vector, and then the gradient vector. Okay, right? So, but just how we say, u is what? Unit vector. So this has length 1. Okay, length 1. Okay, length 1. Cos theta. So the gradient is maximum when? At when? When is this gradient maximum? Which number? When it is the maximum? When does this value maximum? When cos theta is 1. When is cos theta equal to 1? 0. Theta equals 0. Okay, so few things I want you to take note here. You see why we set our directional derivative as, the unit vector as, the direction vector as unit 1. Why? Because this number here doesn't seem to do anything to our gradient. Because this u here doesn't depend on f. So we don't want the direction to affect my gradient. You get what I mean? I can put any u literally. But then this number here will be multiplied just by the length of u. Okay, so I don't want the direction to change my gradient. Okay, to change my information on my surface. Because that's just a choice. Okay, so that's why we set u to be unit length 1. Then we can recover the gradient, the slope. The slope is exactly what we want because this slope tells us about f, something about f. Okay, so you see, when does this slope get the largest? In the direction of u, when you have the same direction as u, when the theta is 0. Okay, when you have the same direction as your f, then you have the largest gradient. Okay, you have the largest gradient, is it? Yeah. Okay. Okay. So if you align your u, okay, to the direction of your gradient vector, you get the most. You get the most. Okay. Let us apply to the god again. So remember how the god climb out the surface or not? You still remember? So do you still remember how the god climb out the surface?
Spinner's rip. When atoms can't function properly, there's a strong bond between mother and
Can
kid.
you see how they climb out the surface? Do they climb out like this? No, right? Where is the steepest direction for the wall? It's in the forward direction, right? So the goat won't climb like this. The goat climb like this, like perpendicular to the direction of the gradient of the vector. Okay, so next time you try. Do you walk up a staircase or not? You walk up the staircase. So if you climb up the staircase directly, it's harder if you climb the staircase sideways. You can try. You can try. Okay? Okay? So try and walk up the staircase sideways. Compare you walk up the staircase directly up. Which one is easier? You can try. Okay? So you try and reduce this angle here. Okay, try and reduce this angle. Alter this cos theta here. If it's away from 0, then cos theta will decrease. Okay. Yeah, you can try. Okay. Directly walk out the staircase is easier, or you walk sideways easier. Think about it. We'll talk again next time. Yeah, see you next week.